step down. But just to be clear what we're doing, I wrote it down. This is s squared big Y minus s times y of 0 minus y prime of 0. Then we have 3 times s times big Y minus y of 0 plus 2 times big Y. Why big Y? Because nobody wants to do algebra in this symbol. I mean, do you want to do algebra on this symbol? I don't want to do algebra on that symbol, because we're soon going to be doing algebra. In fact, already at this stage, what I wrote down is an algebraic equation in big Y and S. So we've traded, this is a differential equation, right, in Y and T. Look at what we have. After the Laplace transform has been taken, we have an algebraic equation in big Y and S. That's much better because we can solve algebraic equations using algebra, right? Yes. You're like, I don't know algebra. Get out! Just get out. No, I'll stop. I will help you, but no, we do need to learn algebra if we don't know it already. Joking aside. So y of 0 is given to be 0, right? And so that's 0. This is 0. This is 1, right? And so what do we got? We've got s squared times big Y minus 1 plus 3s times big Y plus 2 times big Y, 1 over s squared. Great. So let's solve for big Y. That's our goal. Solve for big Y. We've got big Y times what? Times s squared plus 3s plus 2 is equal to 1 plus 1 over s squared, yeah? So now we just have to divide by that, right? And there you go. You got big Y equals to 1 over s squared plus 3s plus 2 times 1 plus 1 over s squared. So we've done the algebra, right? We've done the math. Now we need to go back to the time domain. So here's the deal. We start with y. You take the Laplace transform, it gets you to big Y. Then you take the inverse Laplace transform, it gets you back to y again. So what's the inverse Laplace transform? For example, the inverse Laplace transform of, say, 1 over s minus 3 is a function of time, and it's, well, it's e to the 3t. In other words, to calculate inverse Laplace transforms, rather than going from the left column in table 7.1 to the right, we go the other way. We go from the right column to the left in table 7.1. That's the inverse transform. So look at table 7.1, right? Look at the right column in table 7.1. Do you see this one? Do you see this anywhere in the right column of table 7.1? The red boxed expression. The answer is no, not even close. Are you crazy? Of course not. That's not there. So what do? What's that? We do algebra. That is a safe guess. Almost always in here. Throw algebra at it till it breaks. Okay. Okay, essentially. Now, so what I do when I look at this, I say, okay, so I'm not sure what's the wisest course going forward, but essentially, we're going to be able to see that this is something like a over s plus b over s squared plus c over s plus 1 plus d over s plus 2. This is the partial fractions decomposition of such a rational function, because after the dust settles here, this factors, right? This is s plus 1 times s plus 2, if you hadn't noticed. And so I'm going to be able to find a, b, c, d to decompose that function to that function. I've got 7 minutes. That should be enough time to do that. Let's do it. So the process of inverse Laplace transforming, most of the difficulty is in seeing what you need to do in terms of partial fractions. That's the first level, all right? Next level, there's the discontinuous stuff we'll talk about next time, but let's work through this example. So what we do, I would multiply, let me give this thing a name, star. So let's multiply star, and I can erase my silly example of inverse transform up here. Doesn't matter to us anymore. So multiplying star by s squared times s plus 1 times s plus 2. What's that? What happens when I do that? I get, so I get that term cancels, right? And I'm left with s squared times 1 plus 1 over s squared equals to a times what? As times s plus 1 times s plus 2 plus b times, oh, poor planning on my part. Let me, goodness gracious, I'm going to have to continue down here. Sorry about that. B times s plus 1 times s plus 2 plus c s squared times s plus 2 plus d s squared times s plus 1. So as you multiply the right-hand side of the partial fractions decomposition there by the total denominator, you get this cancellation of everything that's not there. I mean, everything that's there, rather. So like the s cancels with the first one. The s squared cancels with the second one with a b. The s squared and the s plus 2 cancel with the c term. The s squared and the s plus 1 term cancel with the d term. Don't cancel with the d term, rather. I keep saying it backwards. Anyway, it's up here. Okay. Then what? May I recommend plugging in some values, right? So, for example, a nice value to plug, let's multiply this out. Let's multiply that out. Okay. Now let's plug in some values. I don't recommend plugging in 0 into this. Plugging 0 into this, okay. So isn't that funny? Plug 0 into this. Can't plug 0 into that. But this, is always an issue with partial fractions. We're always plugging in the places where the expression's divergent. Yet it works. Why is that? Well, that sounds like a question for my D-term Calculus 2 online. All right, let's see here. S equals to 0, which is 1. I really don't like them. That's not what I was trying to communicate, but okay. I mean, how can I not like them? I don't even know them. 0 plus 1, 0 plus 2. I mean, I've met a couple of them in person. And that's the weird thing about teaching an online course residentially. Your online students come up and shake your hand. It's like, see here. Okay, so apparently 2b is equal to 1. B is equal to a half. Okay, let me stop my jibber jabbering so we can in class. S equals minus 1. Gone, gone, gone. We're just left with this one, which is what? I think it's just c, right? So we get 2 is equal to c, because I got minus 1 squared times 1. Yeah, 2 is equal to c. So we got c, we got b. And maybe I think plugging in minus 2 would be a smart move. Plugging in minus 2 to the left-hand side gives me 5. Over here, gone, gone, gone. Plug in minus 2 here, I get a minus 1 times a 4, which is minus 4d. d is minus 5/4. How are we going to find a? Just plug in any other value, right? Maybe, and you want to be lazy. What's a good value to plug in? We already used 0. Otherwise, I would totally agree with you. 1, I like 1. 1 would have been my choice. So, because 1 gives me 2 on the left-hand side, and over here, 1 times 2 times 3 is 6a. 2 times 3 is plus 6b, right? 1 times 3 is 3c. And then 2 times plus 2d. So a is apparently 2 minus 6b minus 3c minus 2d, all divided by 6. What's that work out to? Oh, I didn't bring my calculator. It's up to you guys. So that's 2 minus 3 minus 6 plus 10 over 4. Minus 3/4, maybe? I don't know. Let's assume it's that for a second, okay? So let me go back to my, because I'm almost out of time here. So go back to my A, B, C, D. What was A? Up to an arithmetic mistake, minus 3/4. B, I think we got right, was 1/2. C was 2. D was minus 5/4. So that's my y. The answer is obtained by inverse Laplace transforms. Inverse Laplace transforms is a piece of cake now that we've done the partial fractions. So y of t equals 2. We've got from the 1 over s, that gives me minus 3/4. From the 1/2, I get plus 1/2 t, I believe. All right. And then plus 2 e to the minus t minus 5/4 e to the minus 2t. There you go. That is the solution to the initial value problem that was stated. No particular solution, no fitting C1 and C2. It's just all done for us in one foul sweeping masterclass in algebra, right? It came at a cost, right? The partial fractions here was a non-trivial algebraic task, which is why we don't just teach this. Sometimes the methods I've been teaching you before are better, but this is a way. So I think it's really, really cool the way the initial conditions get rolled into the transform. Yeah? But anyway, so next time I will show you the really weirder side of this, which we could not have done without this method. Thanks, guys.